Today I'll be talking about the slope and scatter of the stellar mass angular momentum relation. I'm currently a second year PhD student here at ICRA UWA, being supervised by Luca Cortez and Daniel Brushkov. So angular momentum is an important quantity to be studying as it's linked to a galaxy's formation, evolution, and morphology. So in the early universe, dark matter halos are going to interact through tidal torques, which will impart angular momentum on each other. Later, gas will then fall into these dark matter halos, kinematically mix and collapse to form a galaxy. So we know the relationship between a dark matter halo's mass and its specific angular momentum from cold dark matter theory, where we expect it to be directly proportional with this exponent of 2/3 here. And this can be transposed into an equation which relates the stellar mass and stellar specific angular momentum of the galaxy within the dark matter halo, where now we have these two extra terms being introduced, Fj, which is the fraction of stellar specific angular momentum retained by the halos from the stars, by the stars from the halo, and F star, which is the stellar mass to halo mass fraction. So the relationship between stellar mass and stellar specific angular momentum is important to study because it could give us information about how dark matter is transferring angular momentum to the galaxy within. And if we make the simple assumption that this Fj and F star parameters don't vary as a function of stellar mass, then we get this quite simple relation out that the stellar mass is directly proportional to this with the power of 2/3 to the stellar specific angular momentum. Now, this might seem like a fairly simple assumption to be making, but this was actually what was found by Fall in 1983 when they first looked at the relationship between stellar specific angular momentum and stellar mass. And because of this preliminary work that was done by them, I will be referring to this as the Fall relation from here onwards. So this is an example of a Fall relation from some work by Romanowski and Fall in 2012, where we can see some spiral galaxies up here and some elliptical galaxies down here. And they found that the spiral galaxies and the ellipticals both followed a relationship given here, where they found that the elliptical galaxies had 5 times less specific angular momentum on average than their disk galaxies. In contrast, other works such as Posty in 2018 have also studied this Fall relation, where here they found a slope that was a bit shallower of 0.55, which they attributed to a varying Fj and F star with stellar mass. Now, you can also see as well that they have a different range of morphologies in their sample, but they didn't find as much of a spread in their relation with morphology. So it's still quite contended what the slope and scatter of this relation is. And the main reason for this is statistics. So this Romanowski and Fall work only had just under 90 galaxies, and Posty had a similar size sample. So really we need a large sample that's morphologically diverse to be able to distinguish what the solution to this is. So this is where the xGASS sample comes in, which is a gas fraction limited sample with over 1,000 galaxies in a stellar mass range from 10 to the 9 to 10 to the 11.5. And this sample has a wide range of H1 gas fractions, as all of the observations were taken until either H1 was detected or there was a gas fraction limit reached of 2 to 10%. So this is a beneficial sample to use as it's quite large, it has a large range of morphologies as well, and it isn't biased to H1 rich galaxies. So I'll be using a subset of this sample, 564 galaxies, with which we had H1 detections, and we had inclination greater than 30 as well. So in order to calculate stellar specific angular momentum, there's 2 key quantities we need. The first is the surface density profile, which we assume to be a Sirsic mass profile. So we do this by taking 2D structural decompositions of SDSS images, where we've fit in 2D component Sirsic profiles with both a disk and bulge component. We then reconstruct magnitude profiles from these fits and convert these to a mass profile using the Zabetti 2009 light to mass conversion. For the velocity profiles, we assume a constant rotation curve. This is because if we use a unresolved H1 velocity widths, we can increase our sample size. If you want to use resolved kinematics, you have to, it's a lot harder to get a large sample. So we assume that the width of the H1 is the maximum rotation velocity of a galaxy, and we assume that that value is constant for all radii. This has 2 key assumptions. One, that the rotation curve is flat, and secondly, that the bulge is co-rotating with the disk. And we've tested both of these assumptions and don't think that this will affect our results considerably. So here I'm now showing our first full relation where we've got stellar mass of the entire galaxy, so the bulge and disk component, against the stellar specific angular momentum of the whole galaxy. And in this thin black line here, I'm showing the best fit to our data using a Bayesian fitting tool called Hyperfit. And we find a slope of 0.47, which is considerably shallower than a slope of 2/3 that you might expect for the cold dark matter halos, which I'm showing here in the purple dashed line. I also show the blue line, which is the posty work I referenced earlier, and we also have a shallower slope than they do. Our best agreement is at low stellar masses, where our sample has mostly disk galaxies. So we also look at just isolating the disk component of our galaxies. So just looking now at the stellar mass contributed by the disk and the specific angular momentum of just the disk as well. And now our relation is a lot steeper. Again, in this black line is the best fit. And we now get a slope of 0.6, which is much closer to the slope you'd expect for the cold dark matter halos of 2/3. We're also now in much better agreement with the posty work, which also have a version of their relation with just the disk component. And we also get the normalization very close to their work as well, which is quite promising for our work and our methodology, as we have used unresolved kinematics, whereas they use resolved kinematic maps to determine their angular momentum measurements. So we can see that there's already a dependence on galaxy type in terms of this slope. So we also looked at just galaxies where we have a considerable bulge component, which we define to be where the bulge has more than 40%, the mass of the bulge is more than 40% of the total mass. And you can see again in the black line that our best fit relation is very close to the slope of 2/3, still in the purple dashed line. And we get a slope of 0.69 for this one here. If we assume the bulge not to be rotating, which is the kind of converse assumption that we can make, then the normalization of our slope drops a little bit. Sorry, the normalization of our line drops a little bit, but the slope doesn't change considerably. So it doesn't really seem to be too important to our results. So if we combine these three plots here, we see that when you isolate just the morphology, so if you have just a disk component or a bulgy galaxy, you get a slope that's very close to 2/3. However, when we take our whole sample, we have slightly more disk galaxies at low stellar masses and more bulge-dominated galaxies at high stellar masses, which can artificially create a slope that's shallower than 2/3. So we find that the variation in galaxy formation theory isn't needed to explain a slope shallower than 2/3, and instead this can just be due to the variation of morphology across stellar mass. So I've shown that it's important to consider morphology in this relation, and also that in these previous works they found offset relationships for different morphologies. So we wanted to see if there was any correlation between the scatter in this relation and any galaxy properties. So we took each galaxy and took the offset of each galaxy's point from the best fit relation and saw if this was correlated with three key galaxy parameters: bulge to total ratio, H1 gas fraction, and the specific star formation rate. And we found that overall the strongest correlation was with H1 gas fraction. However, if we went and split our full relation into two sections, so below 10 to the 10.25, we saw that so this here is the vertical offset and the H1 gas fraction. We found the strongest correlation with H1 gas fraction at low stellar masses, but at high stellar masses, bulge to total ratio is now slightly more correlated with the scatter in the relation than H1 gas fraction is. If we now go and look at just the disk component again, so this is the disk component for relation I showed earlier, we see now that the scatter of the relation is always correlated with H1 gas fraction at all stellar masses. And that's what you can see here on the right, where we've got the H1 over disk stellar mass against this vertical offset. And you can see the running median here is showing a strong correlation between the two.
You got 1 minute, Jenny.
No worries.
Yeah.
So to summarize, when bulge to total ratio is fixed, the slope of our full relation is very close to 2/3 with offset relationships for different morphologies. However, when we consider our whole sample together, the morphological spread of galaxies at fixed stellar mass creates a slope that's shallower than 2/3. We get a slope of 0.47 in our work. And the strongest correlated parameter with scatter for our full relations is H1 gas fraction. Thank you.
Thank you so much, Jennifer, for that very nice talk. It was very interesting indeed. So we already have a question on Slack by Julia, who asks, if she's wondering if how the disk component is selected in your sample.
Yeah. So in a previous work, which I've adopted, they took SDSS images and fit a 2-component SERSIC profile. So they had a approximately exponential. I think they let the SERSIC parameter vary between 0.5 and 1.5 for the disk component, and then had a somewhat free SERSIC parameter for the bulge component, and fit those using a fitting tool called Profit, and then got out the SERSIC profiles from that. So then I just use the SERSIC profile for the disk and then use that in my calculations.
Right, yeah, thanks for that. Matthew asks, what does the offset between the fall relations for disks and spheroids tell us about the formation of spheroids? If you have any idea on that.
Yeah, that's a good question. I haven't thought about that too much specifically. Yeah, haven't thought about that one too much.
That's all right. Yeah.